Okay, we're going to do the Chapter 3 exam review. Question number 1, 51% of students entering four-year colleges receive a degree within 6 years. Is this percent larger than that for students who play intramural sports? And 115 of the 202 students who played intramural sports received a degree within 6 years. What can be concluded at a level of significance of alpha equals 0.1? So this is going to be a z-test for a population proportion because they do give us a proportion. They tell us that 51% of students entering four-year colleges get their degree within 6 years. And then they give us data about students who play intramural sports. So we're going to be doing a z-test because we're going to be using the normal approximation of the binomial. So we're going to do a z-test for a population proportion. And what are we testing? Is this percent larger than that for students who play intramural sports? So is this greater than 0.51 for students who play intramural sports? So our null hypothesis is that it would equal 0.51. Okay, so we're going to conduct a one proportion z-test on our calculator using this data. So I'm going to share my calculator. Okay, so we're going to conduct a one proportion z-test, which is 5 in our stat tests. And our proportion that we were given was that 51% graduate within 6 years. And the data we were given is that 115 out of the 202 that play intramural sports graduate. And we're interested in, is this proportion 0.51 greater than the proportion that we're getting, or the proportion of the intramural, is it greater than the 0.51? I can't spit it out. And so we're going to calculate. So our Z statistic is 1.6862, and our p-value is 0.04588. Okay. So our Z statistic was 1.6862, and our p-value was 0.0459. Now this p-value, 0.0459, is less than or equal to our alpha. So what do? If the p is low, the null must go. So we're going to reject the null hypothesis. So what is our conclusion? If we reject the null, then we are making the assumption that the data is significant enough to support the alternative. So the only choice of these three that has significant in it is the first choice. The p-value is 0.0459 or 4.59%. This is the probability that we get a value as extreme as we did or more. So if we look at the four choices here, it's not going to be the first or the third. It's either going to be the second or the fourth. And it's the second because the second contains the word population. So that has to be the choice that you have there. If the population proportion of students who played intramural sports who received a degree within 6 years is 51%, and if another 202 students who played intramural sports are surveyed, there would be a 4.5% chance that more than 57 of the 202 students surveyed received a degree within 6 years. Okay, the last part, alpha is 0.1, which is 10%. This is the probability of a type 1 error. A type 1 error is you reject the null when it's true. So you're rejecting the null and saying that the data supports the alternative when that's actually not the case. So which of the 4 choices here? Well, it's not going to be the top 2. It's going to be either the third or the fourth. And the last sentence in that, it says, if the population proportion of students who played intramural sports who received a degree within 6 years is larger than 51%, and another 202 students who played intramural sports are surveyed, then there would be a 10% chance that we would end up falsely concluding that the proportion of all students who played intramural sports who received a degree within 6 years is equal. No, that's not it. It would be, we would falsely conclude that it's actually larger than 51% when it isn't. We would accept the alternative when it's actually not true. All right, problem 2. The recidivism rate for convicted sex offenders is 14%. A warden suspects that this percent is different if the sex offender is also a drug addict. Of 389 convicted sex offenders who are also drug addicts, 35 of them became repeat offenders. So this is some kind of proportion because they're giving us the number of successes, whether you think that repeat offenders are successes or not, but they're giving us the number of successes out of the number of trials, 389. What can be concluded at alpha equals 0.01 level of significance? So we are going to do a test of a population proportion. So it's going to be a z-test of a population proportion. So what's our null and our alternative hypothesis? He says that he thinks that it's different than the average or the proportion, excuse me. So his alternative is that it's different than 0.14. And so our null would be that it is 0.14. Okay, so we're going to go conduct a 1 proportion z-test. On our calculator. Okay, so let's go to our calculator. So we're going to go stat, tests, 1 proportion, z-test is number 5. Okay, the proportion that we got is 14%, 0.14, and then his data says of 389 convicted sex offenders who are also drug addicts, 35 of them became repeat offenders. So we had 35 successes out of 389. And we're interested in if the proportion is different. Our alternative hypothesis was not equal to. So we're going to calculate. So our z statistic is negative 2.8435, and our p-value is 0.0045. So let's go write that down. Our z statistic is negative 0.28435. And they do say to 3 decimal places, so I'd round that up to negative 2.844. And our p-value was 0.0045. They tell me to write that to 4 decimal places. Okay, so what was our alpha? Our alpha is 0.01. So this is less than. Our p-value is less than or equal to our alpha. And if our P is low, our null must go. So we're going to reject our null hypothesis. So our data is significant enough to reject the hypothesis that it's 14%. So we're going to say that the data supports the conclusion that it's not 14%. Okay, so we only have one that says significant, so it has to be the second choice. Okay, interpret the p-value. Our p-value was 0.0045, which is 0.45%. And the p-value is the probability that we get a value that extreme or more. So it's not going to be the first two. So it's going to be this one of the second, either the third or the fourth, and it has to be the third because the third contains the word population. Okay, interpret the level of significance. Our level of significance was 1%. So that is the top percentage or the probability of a type 1 error, which is rejecting the null if it is actually true. So you're concluding that the alternative is true when it actually is not. So it's either got to be the first one or the third one. So we falsely conclude the proportion of all convicted sex offender drug addicts who become repeat offenders. Bleh, I can spit it out. It has to be the first one because it's the one that says that we're rejecting the null and accepting the alternative, that the proportion is different than 0.14. Okay, question 3, find a interval. So we're going to use a 1 proportion Z interval because we are looking at proportions and we're looking for a confidence interval. So that's what we're going to use. And it does tell us that we have to calculate X, excuse me, because I don't know what X is. They give me P hat and they give me N, but they don't give me X. And I do need that information to be able to put this in my calculator. So we're going to take 240 and multiply it by P hat. And that's going to give us 72. So X is 72, N is 240. And we can go put that in our calculator. So a 1 proportion Z interval. So stat tests a 1 proportion Z interval. You just scroll down. 1 proportion Z interval is A. And I need to put in X, which is 72. And N, which is 240. And we're using a 95% confidence level. So we're going to leave that alone and calculate. So our interval is going to be from 0.24202 to 0.35798. So 0.2420. They tell me to round it off to 3 decimal places, so I don't really need the 0. To 0.358. All right, problem 4 is the average time to complete an obstacle course different when a patch is placed over the right eye than when a patch is placed over the left eye. 8 randomly selected volunteers first completed an obstacle course with a patch over one eye and then completed an equally difficult obstacle course with a patch over the other eye. The completion times are shown below. Left means the patch was placed over the left eye and right means the patch was placed over the right eye. Assume a normal distribution. What can be concluded at the alpha of 0.05 level of significance? For this study, we would use, okay, this is matched pairs because we're comparing one person with a patch over the right eye, and then the person completes the same obstacle course with a patch over the left eye. So these are dependent pairs, and we're comparing the difference. So that's what we need to calculate. We need to calculate the difference. And we're going to run a t-test on the differences. And I'm going to calculate right minus left. And I'm going to put that in a list, and then I'm going to run a t-test on that set of differences. So we're going to run a t-test on two dependent or paired, I don't remember what the drop down says, two paired sets of data. I don't remember what the drop down says. Okay, and we're going to do a t-test on the differences. So I'm going to real quick calculate those. So I have right minus left. So I'm going to have -2, 1, -1, -2, -1, -1, 1, and 3. And so that's the data that I'm going to put in my calculator. And what are my two hypotheses? Well, if I'm looking at the difference between these two sets of data, then I'm going to look at the difference being 0 or the difference not being 0, because they just want me to know, or me to test if there's a difference between the two values. Okay, so I'm going to run a t-test on these differences. So I'm going to share my calculator, and I'm going to put this data in a list. And I'm going to put it in L3 because L1 and L2 I'm going to use later. So I'm going to put it in L3. So I have differences here. So I have -2, 1, -1, -2, -1, -1, 1, and 3. Okay, so I have my differences, right minus left, in my list. So I'm going to go run a t-test on that list. So I'm going to get out of here, go back in my stat menu, go over to test, and I'm going to run a t-test. And I'm going to run the t-test on my data that I have in L3. And our null hypothesis is that the mean difference is 0, and that the alternative is that it's not equal to 0. So let's change that to L3 because that's where I put my data. And we are going to use not equal to. All right, so my t statistic is negative. Well, that's not correct. I have made a mistake somewhere. Let me check my differences again. -2, 1, -1, -2, -1, -1, 1, and -3. Well, that would be a problem. So in real time, you're going to get to see me fix this. So I'm going to go back to my lists, and I'm going to fix that last difference. It should be -3, not +3. 48 minus 51 is -3. All right. Let's try that again. So stat tests, t-test number 2, go calculate. That looks better. So my t statistic is -2, and my p-value is 0.0856. So we have a t statistic of -2, And the p-value, they say to 4 decimal places, is 0.0852. So what was my alpha? My alpha is 0.05. So my p-value is greater than or equal to alpha. 0.08 is bigger than 0.05. So what do? If the p is high, the null must fly. So we fail to reject. So we can't conclude that the differences are not zero. We can't conclude there's actually a difference in what I they cover up. So which of these 4 is correct? Well, it's not going to be this one because there isn't sufficient evidence to reject. So it can't be the last one. There is not sufficient evidence to reject. And it's not statistically significant. So it has to be the first one. At alpha equals 0.05, there is insufficient evidence to conclude that the population mean time to complete the obstacle course with a patch over the right eye is not the same as when a patch is over the left eye. Okay, problem 5. Does it take more time for seeds to germinate if they are near rock music that is continuously playing compared to being near classical music? The 46 seeds that were exposed to rock music took an average of 25 days to germinate. The standard deviation was 11 days. The 52 seeds that were exposed to classical music took an average of 20 days to germinate. The standard deviation for these seeds was 10 days. What can be concluded at an alpha equal 0.1 level of significance? So we're comparing something here where it looks like we're comparing 2 population means, because they do give me the average time for these seeds to germinate. So I'm going to be doing a t-test for 2 independent population means, because they're completely 2 independent groups. One's being exposed to rock music, the other's being exposed to classical music. So we're doing a t-test for differences of 2 independent population means. Okay, so what's our null and alternative hypothesis? Now, our alternative is that it takes longer for the rock music than the classical music. So we're going to look at mu sub r is greater than mu sub c. And so our null is just that there's not any difference in the 2. Okay, so we're going to conduct a 2-sample t-test. And I do know it's a t-test. I probably should mention this. There's nowhere in here they give me any population standard deviations. So I'm going to use a t-test for this instead of a z-test. All right. So let's go to our stat test. And we're going to do a 2-sample t-test, which is number 4, 2-sample t-test. Okay, and we're going to do it on stats that we were given, not data. Okay, and so our X bar, we had 25 out of the 46 germinate with a standard deviation of 11. So let's put that in there. We had 25 on average, when an average of 25 and a standard deviation of 11, and our sample size was 46. It's not a proportion, we're looking at averages. So the average number of days to germinate was 25. In the second group, the classical music, it took on average 20 days for the seeds to germinate with a standard deviation of 10, and our sample size was 52. And we are interested in, is the classical music less than the rock, or is the rock greater than the classical? So we're going to do greater than. Okay. So our T statistic is 2.3431. Our p-value is 0.0106. So our test statistic is T is equal to 2.343 to 3 decimal places, and our p-value is 0.0106 to 4 decimal places. And our level of significance that we're testing at is alpha equals 0.1. So our p-value is less than or equal to alpha. So we're going to reject the null hypothesis. There does appear to be, or appears based on our data, that it takes longer for the seeds that are exposed to rock music to germinate as opposed to those exposed to classical music. I can't talk really. So which of these 4 is correct? It is statistically significant, so we don't want that, and we don't want that, because our data does show significance statistically that the rock music is greater than the classical music. Okay, so which one is it? I do believe it is the first one. It's the first one because it says the time for seeds exposed to rock music to germinate is more than. And then the third one says, seeds are more than the mean germination are exposed to classical music. So this one is sufficient as conclude. Now, to conclude that the mean germination time for the 46 seeds exposed to rock music that were observed is more than the mean germination time for the 52 seeds that were exposed to the classical music were observed. It is showing us that there's evidence to conclude that the population mean time for the rock music is more than the classical music. All right. P-value, our p-value is 0.016 or 1.06%. That is the probability that we get a value that extreme or more. And it has to be this one because it contains the word population. All right, so our level of significance, alpha was 0.1, which is 10%. And this is the probability of a type 1 error, that we reject the null when it's true, which means we accept the alternative when it's false. So we would accept that the time it takes for the rock music seeds to germinate is longer than the classical music seeds, and that's not the case. So it's either the first one or the second one. If the population mean time for seeds exposed, I'm just going to run through this to get to the end, that the population mean time for seeds exposed to rock music to germinate is more, it has to be this one, because that is what we were testing. We were testing if it's more. We weren't testing that they were different. And that's what this one says, that they differ from each other. So it has to be the first one. Okay, problem 6. A retailer wants to see if a red sale sign brings in more revenue than the same sale sign in blue. The data below shows the revenue in thousands of dollars that was achieved for various days when the retailer decided to put up the red sale sign, and days when the retailer decided to put the blue sale sign up. So we have the data for red and blue. Assume that both populations follow a normal distribution what can be concluded at the alpha equals 0.10 level of significance. So what are we going to be doing here? We're trying to detail if red is bigger than blue. So this is going to be comparing two independent population means. Because they should be independent of each other. You're not doing any kind of before and after. And by the way, I know I can't do a test on differences because I have more data in the red category than I do in the blue. So we can't do differences. I have to have the same number of data values in each group to do differences. So this is two independent population means. So we're going to do a two sample t-test. Okay, so what's our null and our alternative? Well, the null would be that the red and the blue are the same. But what we're testing is the red bigger than the blue? Do you get more sales on average if you put up a red sign compared to a blue sign? And I believe the test actually uses mu1 and mu2, which is fine because I'm going to put red in a list and I'm going to put blue in a list. And then I'm going to run the two sample t-test. And I do already have this data in L1 and L2. So I'm going to conduct a two sample t-test on that data. Two sample t-test is number 4 on my data. And I have red in L1 and blue in L2. And I'm interested in is L1 bigger than L2? So I am interested in mu1 is bigger than mu2. So my t statistic is 1.2161. My p-value is 0.12. So my t statistic is 1.216. And my p-value is 0.1205. So my p-value is greater than or equal to my alpha. So we're going to fail to reject. Okay, so which of the 4 choices, my final conclusion? So the results are statistically insignificant because we're failing to reject the null. So we've got 2 that say statistically insignificant. And what are we concluding? So there's insufficient evidence to conclude that the population mean revenue on days with a red sales sign is more. It's this one. We don't have sufficient evidence to conclude that the red sign is more, the sales resulting from a red sign are more than the sales resulting from a blue sign. Okay, what's our p-value? Our p-value was 12.1% if we write it as a percentage. And the p-value is the probability that we get a value that extreme or more. So it's not going to be the last 2. It's got to be this one. The ones that contain the word population, it's that one. Okay, interpret the level of significance. The level of significance was 0.1 or 10%. And that is the probability of a type 1 error. That we reject the null when it's true. So if we reject the null, that means we conclude the alternative that the red sign, the number of sales when you put out a red sign is greater than the number of sales when you put out a blue sign. So it's not this one, not that they differ. It's this one, that the red sign, there's more than the blue sign. Okay, and then last one, last part of this, we're going to calculate a 90% confidence interval. So we're going to use a 2-sample t-interval, which is in your test menu. So let's go to our calculator. So we're going to go to our statistics menu, our test menu, and we're going to find a 2-sample interval, not an interview, 2-sample t-interval, which is 10. Okay, and it is already on my data, L1 and L2, and my confidence level is 0.9. So let's change that. So my confidence interval is from negative 0.2361 to 1.3272. So let's put that in. We have negative 0.2361, and it's the difference in mu1 and mu2. And that's 1.327, I believe is what it was. All right. Problem 7. Are Republicans more likely than Democrats to display the American flag in front of their residence on the 4th of July? 437 of 631 Republicans surveyed display the flag on the 4th of July, and 430 of 639 Democrats surveyed display the flag on the 4th of July. What can be concluded at the alpha equals 0.1 level of significance? Okay, so we're comparing two proportions. So this is a 2-proportion z-test. And I know we're comparing 2 proportions because they give me the number of successes out of the number of trials. And when they give me successes out of trials, that is binomial. And so we're going to use a proportion, and we're going to use the the normal distribution, a z-test, to approximate the binomial. So we're using a 2-proportion z-test. And what's our null and our alternative? They want to test if the number of Republicans that display their flag, the proportion, excuse me, is greater than the proportion of Democrats. So we're going to go put this data in our calculator. So the first group, the number of Republicans, there were 437 out of 631, and the Democrats, there were 430 out of 639. Let's go share our calculator. Okay, so go stat, test. We're going to do a 2-proportion z-test. 2-proportion z-test is number 6. And we have 437 Republicans out of 631 flew the flag on the 4th of July. And we had 430 Democrats out of how many were surveyed? 639. And we're interested in, are the Republicans, which are the first group, X1 and N1, greater than the second group, which is Democrats, which is 430 and 639. So we are interested in if P1 is greater than P2. So our Z statistic for this test is 0.751, and our p-value is 0.226. Let's go write that down. Our test statistic is Z equals 0.751. And our p-value was 0.226. Our p-value is greater than our alpha. So if the p is high, the null must fly. We fail to reject the null. So we can't conclude that more Republicans flew the flag on the 4th of July than Democrats. So it's going to be not this one, not that one, because the data isn't significant. So it's either the 3rd or the 4th. And it's got to be this one because what we tested is that it's greater. We didn't test the equal. We didn't test equals, which was the 4th one. All right, p-value, our p-value is 0.226. So as a percentage, that's 22.6. That is the probability of us getting a value that large or more. It's not going to be the 2nd or the 3rd one. So it's going to be either the 1st one or the 4th one. And it's got to be this one. If the percent of all Republicans who display the American flag in front of their residence on the 4th of July is the same as the percent of all Democrats who display the American flag in front of their residence on the 4th of July. And if we sample another 631 Republicans, 639 Democrats, there would be a 22.62% chance that the percent of the surveyed Republicans who display the American flag in front of their residence on the 4th of July would be at least 2% more. And the 2% more comes from the proportions that are calculated on your calculator. All right, interpret the level of significance. Alpha was 0.1 or 10%. And again, this is the probability that you reject the null when it's true. So you're accepting the conclusion that there are more Republicans than Democrats displaying the flag when that's actually not the case. So we're going to look at these. If the percent of Republicans, do you believe it's this one? So this not this one because it's got the word differ in it. So it's going to be this one because it's greater. That's what we tested. Okay, let's get some easy ones in here. Problem 8. A 95% confidence interval for the mean was computed with a sample size of 100 to be 10 to 14. Then the error is plus or minus 2. And that is true. The mean can be calculated using the confidence interval by taking the average of the lower limit and the upper limit and dividing that by 2. So if we take, let me write that a little neater, 10 plus 14, and we divide that by 2, that's going to be 12. And 10 is 12 minus 2, and 14 is 12 plus 2. So the error then would be plus or minus 2. All right, question 9. If the sample size is increased and the standard deviation and confidence level stay the same, then the margin of error will also be increased. Okay, so the formula that you have for the error bound of the mean is Z sub alpha over 2, which depends on your confidence level, times sigma over the square root of n. So if we increase the sample size, if sample size is increased, then the EBM will go down. because if the denominator of a fraction gets bigger, then the fraction gets smaller. So this is false. If the sample size is increased and the standard deviation and confidence level stay the same, then the margin of error will also be increased. That is false. If we increase the sample size, the error bound of the mean actually goes down. So I've had some issues apparently with the PDF that I made for this particular review. And I'm not sure what happened, but the second half of the test has been cut off. So I'm going to open my Open Math and read the question, and then we'll come back over here to the PDF and we'll put that information in the PDF. So I'm going to go open my Open Math test. All right, so the answers are going to be on, you're going to be able to see the answers before I actually do the problem, but that's okay. All right, question 10. If n is equal to 11 and x bar is equal to 30 and s is equal to 5, construct a confidence interval at a 90% confidence level. Assume the data came from a normally distributed population. Give your answers to 3 decimal places. So this is just a confidence interval. So we're just going to go over to our stat menu and our test menu and create a confidence interval for the mean. Okay. So stat, tests, and we're going to do a t-interval. And we're doing a t-interval because they didn't give me sigma. So we're going to do number 8, and then just put those stats in that they gave me. Okay, so x bar was 30. And standard deviation was 5. And the sample size was 11. And we're constructing a 90% confidence interval. So we get 27.268 to 32.732. So problem 10, we had 27.268 to 32.732. Okay, problem 11. Problem 11, you're interested in finding a 98% confidence interval. So now you're just going to do it on data. You're going to do exactly the same thing that you did before, but now you're going to do it on a set of data. You're interested in finding a 98% confidence interval for the average commute that non-residential students have to their college. The data below show the number of commute miles for 14 randomly selected non-residential college students. Round answers to 3 decimal places. So I'm going to go put this information in my calculator, and you do see that this is going to be a t-distribution because nowhere in here do they give me a sigma. So we're going to use a t-distribution. Okay, so I'm going to go stat, tests. We're going to do a t-interval, number 8, but this time we need to do it on data. And I guess I need to go put my data in. So let me get out of here and go stat, edit, and I'm going to put this in L4. So I'm just going to put that data in. So we have 27. Eight, 14, 25. Okay, last number. Let me make sure I have all those in. So I'm just going to scroll back up, make sure I have all that data in. So 27, 8, 14, 25, 20, 19, 26, 17, 6, 25, 21, 11, 28, and 6. So I'm good to go. So I'm going to get out of here. Well, it helps if you hit the right button. Okay. Now get out of here. Second quit. Okay, stat tests. We're going to do a t-interval on the data that I put in L4. And we're going to be running a 98% confidence interval, 0.98. So we get from 12.477 to 23.666. So our t-interval was from 12.477 to 23.666. Okay, and if you'll look at the second part of this question, it asks you if many groups of 14 randomly selected non-residential college students. Okay, the first one's going to be the confidence level, 98%, because if we run this test over and over and over again, we are 98% confident that the true population mean would be somewhere in between those two values. So that's about 98% of these confidence intervals would actually contain that true population mean. And 2% wouldn't. If 98% would, 2% would not. Question 12. A news group is interested in constructing a 90% confidence interval for the difference in the proportions of Texans and New Yorkers who favor a new green initiative. Of the 547 randomly selected Texans surveyed, 397 were in favor of the initiative, and of the 549 randomly selected New Yorkers, 467 were in favor of the initiative. With 90% confidence, the difference in proportion of Texans and New Yorkers who favor the new green initiative is between. So I need to run a 2 proportion Z interval. This is a proportion because they're giving me the number of successes, the number of people that were in favor of this initiative out of the number of trials. So this is binomial, it is a proportion. So we're going to be running a 2 proportion Z interval. Okay, so let's go do that. So stat tests 2 proportion Z interval. Which is B. And then we just put in the information. So I had, of the Texans, I had 397 out of 547. And of the New Yorkers, I had 467 out of 549. And we're constructing a 90%, 0.9. So our interval is from negative 0.165 to negative 0.0847. So problem 12, we did a 2 proportion Z interval. because we are looking at the normal distribution approximation to the binomial, and we get negative 0.165 to negative 0.0847. Okay, problem 13. Oh, a nice easy one. You're performing a left-tailed test with a test statistic z equals negative 1.4. Find the p-value. So you're doing a left-tailed test. The z value is negative 1.4. That is the area under the curve to the left, because it's left-tailed. So the p-value is the area under the curve. And I can find the area under the curve using a normal distribution. So this is going to be a normal CDF. And our left bound is going to be that number way to the left, which we're going to use negative 1 e to the 99. And our right bound is going to be the negative 1.4. And this is a standard normal distribution, so the mean is 0 and the standard deviation is 1. So let's go calculate the p-value. So we're going to go to our distributions. Haven't been there so far. We're going to do number 2, a normal distribution. The lower bound is negative 1 times 10 to the 99. Our upper bound was negative 1.4. So our p-value is 0.0808. All right, problem 14. I believe problem 14 is a two-tailed test. You are performing a two-tailed test. Alpha is 0.1 and your test statistic is z equals 2.03. Do I reject or fail to reject? Well, obviously I reject, but let's go find out why. Okay, so let's draw this. I'm a big proponent of drawing a picture. The z is 2.03, but this is two-tailed. So you got another tail over here. So the p-value, actually half the p-value is right here. So that's half the p-value. The other half is in the other tail. So half the p-value is a normal distribution. It's the area under the curve from 2.03 to infinity. So it's a normal CDF. 2.03 to 1 times 10 to the 99, 0, 1. So the p-value then is twice this. 2 times the normal CDF, 2.03, 1 times 10 to the 99, 0, 1. Okay, let's go calculate that. So we're going to do our distributions, the normal distribution number 2, from 2.03 to 1 times 10 to the 99, 1 E99. So we get 0.021178. We're going to multiply that by 2. So times 2. That takes my answer. I just calculated and multiplies it by 2. So 0.0423. So our p-value, and I really only need, a couple of decimal places there. P-value is 0.04. So what was our alpha? Our alpha was, what was our alpha? Alpha was 0.1. So since the p-value is less than alpha, we're going to reject. The p is low, then almost go. Problem 15. Poverty in Alaska versus Hawaii. If we have 21 out of, so this is binomial because they're giving us a proportion out of, a proportion which is a number of successes out of the number of trials. So this is going to be a proportion. We are comparing two proportions, Alaska and Hawaii. So this is going to be a two proportion z-test. Okay, poverty in Alaska versus Hawaii. If we have 21 out of 330 families in Hawaii that were below the poverty time, I think that's poverty line. I think we got a typo in the problem. And if we randomly, two typos, randomly select 330 Alaska families, we find 38 families below the poverty line. At a 5% level significance level, do the data provide sufficient evidence to conclude a difference? So our alternative hypothesis then would be not equal to, which you can see in the answer there. A difference in the proportion of families below the poverty line for Alaska and Hawaii. So our null hypothesis would be that there is no difference. They're equal to each other. The proportions are. And our alternative would be that they aren't equal to each other. So we're going to conduct a two proportion z-test. Okay, so stat test. Two proportion z-test is number 6. And what information do we have? We have 21 out of 330 families in Hawaii were below the poverty line. So let's put that in. 21 out of 330. In Alaska, it was 38 out of 330. And we're testing if they're just not equal to each other. All right, so our z statistic is negative 2.3193, and our p-value is 0.0204. So we got to, let's go ahead and write down the null hypothesis and the alternative. So our null hypothesis was that there was no difference in the poverty level in Alaska and Hawaii. And our alternative was that there was a difference in the two proportions. We got a z-value of negative 2.3193 and a p-value of 0.0204. That p-value is less than the alpha value. So if the p is low, the null must go. So we're going to reject the null hypothesis. So there does appear to be a difference in the poverty level in Alaska and Hawaii. So let's go back and look at the problem. So the correct decision is to reject the null hypothesis. So there's enough evidence to conclude the poverty rate in Alaska and Hawaii are different at this significance level. Okay, so let's go find a 95% confidence interval for the difference in the proportions. So we're going to go find a two proportion z interval. So we're going to go stat tests 2 proportion Z interval. And our data should still be in there when we do that. And it is. We have the Hawaii data in X1 and the Alaska data in X2. And what was our confidence level? We want to do a 95%. So let's change that to 0.95. So we get from negative 0.0949 to negative 0.0082. So our interval is negative 0.0949 and negative 0.0082. Okay, problem 16. Suppose the results indicate that the null hypothesis should not be rejected. Thus, it is possible that you get a type 2 error. Given the only way to decrease a type 2 error, the only way is to increase the sample size. You can do things for a type 1 error, like you can change alpha, things like that, to decrease the probability of a type 1 error. But the only way to decrease the probability of a type 2 error is to increase the sample size. So that's the answer to problem 16. So increasing sample size decreases the probability, the chance of a type 2 error. Okay, problem 17. A 2011 Gallup survey based on telephone and face-to-face interviews with 4,220 adults in China aged 15 and older suggests that 30% smoke regularly or occasionally. The following is also noted. One can say with 95% confidence that the maximum margin of sampling error is 2.1 percentage points. Which of the following is true based on the results of the survey? And as you can see, it's the last one. Because it's the last one because that's what a confidence interval does for us. A confidence interval gives us an interval over which we are confident that our true population proportion would be between. So if we have a 95% confidence interval, we are 95% confident that somewhere between the 30% minus the margin of error, sampling error, which would be 27.9, to 30% plus the sampling error, which is 2.1, so 32.1, we would be 95% confident that between 27.9 and 32.1% of all Chinese adults smoke. So let's go write that down. So we have 30% plus or minus that sampling error. So we have 27.9 to 32.1%. So the true population proportion is somewhere in between. Okay, problem 18. Okay. Nationally, patients who go to the emergency room wait an average of 7 hours to be admitted into the hospital. Do patients at rural hospitals have a higher waiting time? The 12 randomly selected patients who went to the emergency room at rural hospitals waited an average of 8 hours to be admitted into the hospital. The standard deviation for these 12 patients was 2 hours. So we're going to be doing a t-test on population means because we're not given any kind of sigma here. We're given S, the sample standard deviation. What can be concluded at the alpha equals 0.1 level of significance level of significance? So we are going to do a t-test for population means. And we're interested in, do the rural people have to wait longer than the 7 hours that we have on average? And we have data from the rural hospital to test against. So let's go write this stuff down. So we're going to be doing a t-test for population means. And our null hypothesis is that it takes, or the average wait time is 7 hours. The alternative is that it's greater than that. If you are in a rural hospital, you're waiting longer than 7 hours. Okay, so we're going to go put this information in. Our sample, we had 12 people sampled. The average wait time was 8 hours, and our standard deviation was 2. So let's go run a t-test. Okay, so we're going to go stat tests. Going to do a t-test number 2 on our statistics. The average weight was 7, but for our sample, we had an average wait time of 8 hours and a standard deviation of 2, and we sampled 12 patients. And we are interested in whether or not this is greater than, is mu 8, or the mu for our sample, greater than 7 hours. Okay, greater than, and then calculate. So our t statistic is 1.732, and our p-value is 0.0556. So t is 1.7321. P is 0.0556. So our p-value, what was our level of significance? I can't remember. Our level of significance was 0.1. Let's write that down. So alpha is 0.1. So our p-value is less than our alpha. 0.0556 is less than 0.1. So if the p is low, we reject the null hypothesis. Okay, so let's go back over to the test, review, and of the 4, which one does it have to be? Of the 3, excuse me. Well, it's not this one. It's not the second one, because we rejected the null. So the data, the information that we have is significant. So it can't be the second one. The data suggests the population mean is significantly higher than 7 at alpha b equals 0.1. So there is statistically significant evidence to conclude that the population mean waiting time to be admitted into the hospital from the emergency room for patients at rural hospitals is higher than 7 hours. It would be the first one. Okay, problem 19. A 2011 survey by the Bureau of Labor Statistics reported that 91% of Americans have paid leave. In January 2012, a random survey of 1,000 workers showed that 89% had paid leave. The resulting p-value is 0.0271. Thus, the null hypothesis is rejected. It is concluded that there has been a decrease in the proportion of people who have paid leave from 2011 to January 2012. What type of error is possible? Well, if you reject the null, the type of error you get is a type 1 error. A type 1 error is rejecting the null when it's actually true. So if you reject the null, the only type of error you can commit is a type 1 error. Okay, problem 20. Which of the following would result in the narrowest confidence interval? Well, if you remember from the formula we wrote down just a little bit ago, the error bound of the mean is found by taking z, multiplying that times sigma, and dividing that by the square root of n. So what decreases the confidence interval, gives you the narrowest confidence interval, would be the biggest sample size. So you have two, the first choice and the last choice, that have the largest sample size. What also will decrease the size of your confidence interval is decreasing the confidence level. So the smaller your confidence level, the narrower your confidence interval. The larger your confidence interval, you have to widen up the confidence interval, the confidence level. You have to narrow up, you have to widen up the confidence interval. I'm getting all mixed up. But anyway, so it would be the largest sample size with the smallest confidence level, and that would be the first choice. And that concludes the review.